Good evening, everyone. On behalf of the IEEE Industry Application Society Student Branch Chapter of the University of Moratuwa, it is my pleasure to welcome you all to the very first workshop of OctWave 3.0. Thank you for taking the time to join us today. We are delighted to see so many enthusiastic participants eager to begin their journey into the exciting world of artificial intelligence and machine learning. Whether you're completely new to AI or looking to strengthen your fundamentals, today's session is designed to give you a strong starting point for the exciting journey ahead. Without further delay, let's move on to today's session. It is my privilege to introduce today's speaker, Mr. Navindu De Silva. Mr. Navindu is currently a PhD student at the School of Computing, National University of Singapore, where his research focuses on multi-agent systems, natural language processing, and reinforcement learning. We're truly honored to have him with us today to share his knowledge and insights on Introduction to ML. Please join me in extending a warm welcome to Mr. Navindu De Silva. We're honored to have you with us today.
Thank you so much for your introduction. And hello, everyone. Welcome to the session on Introduction to Machine Learning. I hope to give you a background coverage on what is meaning by machine learning, and hopefully give some value and some to cover some important aspects that will be useful for your competition. So I'll start sharing my screen. I hope you can see my screen, and am I audible?
Yes, you are audible, and we can see the screen.
Okay, thank you so much. So let me start off the session. So hello, everyone. So this is the Introduction to Machine Learning session. So we'll be covering some aspects on what is meaning by machine learning, what are the types of machine learning, and also we'll be looking at how data has been processed to be applied for machine learning. And then we'll cover through the workflow process and then the applications. So I'll be having these 5 main sections during my presentation, and I'll be having a small Q&A session to answer any questions in the middle part, and then another Q&A session at the end as well. But if you have any questions that you want to ask during the session, please feel free to unmute yourself and ask so that I can answer there, and if you can clarify your doubt there itself. So moving on. So first we will define what do we mean by machine learning and how does it relate to the overall landscape of AI and machine learning and deep learning concepts. So we are very familiar with the word AI, artificial intelligence, which has been thrown around a lot these days. And in general, if you had to define what we mean by artificial intelligence, it's the sort of the pursuit to develop computer systems that are capable of performing tasks that typically require human intelligence, such as reasoning, learning, problem solving, perception, and decision making. And there are many multiple ways that we can try to approach to reach artificial intelligence. So one of those methods is machine learning. So to understand how does machine learning fit into this landscape of AI, so if you consider the overall domain of AI, the Venn diagram, machine learning would be the subset of the AI systems that can enable systems to learn from the data. So the specialty of machine learning is that we try to learn from data sets and we try to use those experiences to be able to understand how to perform. And then thereafter, there are also a concept known as deep learning, which is a subset of machine learning that uses neural networks, a special type of mathematical optimization, which will try to learn more complex patterns, and especially with large amounts of data. So if we try to look at how these different AI applications and domains are intersecting, in AI, we can have different items such as chess robots, navigation systems, and AI assistants like ChatGPT or some coding assistance, which most software engineers use, like Claude Code or Cursor. But in ML, what we specifically look at is we try to learn patterns from the data to make predictions, such as price prediction, where we try to predict the price of a certain item. And then we try to recommend items for people as well. So we are trying to predict what a person might like, and even classifying what we can predict, whether we can predict whether an item belongs to which class or category. And going even further, we have deep learning methods, which are more complex, using neural networks and more advanced machine learning technologies, such as transformers and so on. So we see applications of those being used for face recognition, text and image generation, such as ChatGPT or Gemini, and so on. So to understand what machine learning means, I use a definition that was given from an old textbook by Tom Mitchell. And what it says is, machine learning is basically a computer program that is set to learn from experience with respect to some class of task T and performance measure P if its performance at task T as measured by P improves with experience P. So there's a lot of terms and definitions in here, but what we try to understand is machine learning, a machine learning problem requires three main components. So that is the task. What are you trying to accomplish using this particular task? Then we have the performance. How do we measure that machine learning problem is being successful? And then finally, the experience. What sort of data has been used to improve the performance for that particular task? So it is important to understand that whether we take any machine learning problem, we can try to understand how those three components are working together. So if you take a email spam detection, so automatically now in your computers or your email systems, your system will easily directly identify whether email is spam or not, even before you had seen it. So if you try to define that as a machine learning problem, the task there is then first to classify whether email is a spam or not spam. So it is trying to identify based on the email whether it has to be categorized as spam or not spam. So that is going to be the task. And the performance is whether we can accurately classify that or not. So in an ideal system, we try to go to 100% accuracy, where we can almost definitely accurately identify if an email is spam or not spam correctly. And for this purpose, to get to that highest performance, we use experience, and which is basically a large data set of previously labeled emails. For this purpose, we need to have a set of emails which have been already identified if they were spam or not spam. So machine learning, it's important to understand that we are not doing machine learning as a pure crystal ball prediction. We are using previous data. So any ML problem similarly can be described using these three components here. So to recap what we were discussing under machine learning, it is basically the process to enable the machines to improve their performance on a task by learning patterns from data rather than being explicitly programmed. So if you take email spam detection, we do not have to now give rules saying that if these particular words are there present in the text, it has to be spam. We get the machine learning model and the algorithms itself to identify what sort of characteristics, what sort of features are necessary to identify if an email is highly likely to be spam or not spam. And using these patterns, we try to train a model which can represent all those learned patterns from the data. And thereafter, we use the predictions and decisions from this model. So we use the data and we train using different ML algorithms, which we have to choose. And then we can construct a machine learning model. And using that machine learning model, we only make our predictions and take decisions. So that is it for the introduction and what is meant by machine learning. So in the next section, we'll be covering what are the different types of machine learning that are commonly used in today's world. So we have mainly three main categories which can be used for machine learning. So the first type is called supervised learning, where we try to learn from labeled data to make the predictions. And unsupervised learning, we try to discover hidden patterns in the structure or the unlabeled data. And then finally, the reinforcement learning, where where instead of using labeled or unlabeled data, we are trying to have the agent to interact within an environment and gather information using the rewards that are coming. So we'll dive into more specifically what each category, what each type of machine learning does and how is it performing. So under supervised learning, we can identify that it is an approach where it is mainly to identify the models which can learn using labeled data. And what we mean by labeled data is that there is a correct target output known during the training process or within the data set. So if, for example, when we train the model using supervised learning, we will have the input features, which are basically the characteristics of a particular sample data in the data sample. And we also know the target or the label or the output from that. So here we try to infer one particular specific value, which we believe to be influenced by all the other input features here. So when we try to do the prediction, we are only we only have the input features. We do not know the target label or the output. And our machine learning model using supervised learning aims to try to predict and identify what must be the most appropriate value for the target label or the output. So in a sense, supervised learning, their purpose is to learn the relationship between the X and Y, between the input features and the output, so that the predictions can be made for new unseen inputs. So there are different ways we can also do supervised learning, and that mainly comes down into the types of data that is being used for the process. So for instance, we have regression. So regression will try to predict continuous numerical values. So in here, our output will be a continuous range of numbers. These numbers can be decimals and numbers in a long range. So for one algorithm that can be used to conduct regression is known as linear regression, where specifically we have the data coming within a linear pattern inside our system. So we can try to predict things like house price prediction, which can take continuous values along a large range of rupees or dollar amounts. And using sales forecasting also, we can try to predict maybe how much sales will come in a particular month as well. And these two, we can clearly see their output is going to be a continuous numerical value. But if you consider the other type of supervised learning known as classification, we try to predict a discrete category or a class. So there might not be a large range of output types of outputs that could come here. There could be only a few number of categories. So this could be like a class, like category 1, 2, 3, like that. And most often it will be limited to a small number of categories as well. So it's much more different than the numerical, done by regression, because numerical ones will have a large range of outputs to cover. Whereas classification, you have a fixed range of outputs that could come based on the particular problem you're solving. So a few algorithms that can be used for that is known as logistic regression and KNN, which is known as K nearest neighbors. So for instance, if you try to identify whether a person has a disease or not, is infected or not, we will have basically one class for infected and one class for not infected. So then our target will be to, based on the features of the person's health and their other characteristics, we try to figure out whether he belongs to the class of infected or not infected. So it will be like a binary classification, since there are only two outputs in this particular case. We can also have multi-class classifications as well, where we can sort emails into categories. I think in some emails like Gmail, you can identify that also they categorize your email based on a category as well, such as primary emails or social emails, promotions, updates, and so on. So you can see like in here as well, in the diagram on the right, under k-nearest neighbors, we try to figure out whether a particular data point will belong to which particular class here. And that is how we can use supervised learning to learn different patterns and try to predict according to which is the correct target output value it should belong to. So a key part here with supervised learning is that we know what are we going to predict from our data set. We are given a target variable that we want to predict or identify before we even got that in real world. So the other type, unsupervised learning, is the opposite. It does not have a target variable to be predicted during the training process. So what is then the objective of using unsupervised learning? Unsupervised learning is then important to identify the hidden patterns and relationships or the structures within the data. So even though we do not know a particular target we are going for, we can try to identify patterns and relationships between the other features as well, and even form different insights about the data as well. So for instance, we can do customer segmentation, where using a data set of customers, we can try to identify different groups of customers. So even though in here, we can easily divide customers into classes, in here, under classification, we are given the particular classes. But on unsupervised learning, we are not given the classes. And we ask the machine learning model to identify those classes itself based on the features. So this is a much more different, since it does not know what are the classes, and we only give that we want to separate these particular data points and people into different classes. So it's a form of clustering. That has been done here. And also document grouping, market-based analysis, and even data visualization and compression as well. So we can also see different common categories of unsupervised learning as well. So for instance, we can see the common categories. One is clustering. So we try to group similar observations or similar data points together. So for instance, we can see here, this is a sample example of k-means clustering, where all the data has been now clustered into groups by the different colors. So we can see here in the green cluster, all these particular data points given, identified within the green cluster, can be categorized as one group of customers. And maybe this blue set will be another group. And each of these sets has their own distinct features that can separate them from each other. So this tries to give us a sort of a generalization of maybe we don't have to describe every single type of person, but now we can say that these type of data points belong to some particular category as well. And we can even do clustering as a hierarchical way, where we can have subcategories also within a particular cluster as well. And we can also use unsupervised learning for dimensionality reduction. So we try to reduce the number of features while preserving the important information. So if we could sort of like visualize the data within a 3D space, a method such as PCA, principal component analysis, or factor analysis, can try to reduce the number of features into a 2D space. So this is useful because in some cases, we try to reduce the number of features that are required for a particular problem. So instead of showcasing our different data features within large number of features, we can try to reduce them into 2 or 3 simple axes as well. So we can easily see what are the most important features that are relevant for that to identify those groups and clusters here. So again, we can see here, we are trying to identify different patterns rather than trying to predict something special here, some known value. We are trying to use them to identify some relationship between the data, which was probably not visible or directly known at the start. The other type of machine learning is known as reinforcement learning. So reinforcement learning is one of the most new areas which are now getting high demand and focus now in these days. So in here, what it tries to do is that it has an agent which tries to learn by interacting with the environment, where it can try to receive rewards or penalties based on its action. So if I try to explain using the diagram, our agent is basically like an actor within a particular environment. And the agent's purpose is just to choose what action to do. So once it performs an action, it will do some change in the environment, or you can even assume like the agent will be moving around this environment based on this action, going up or down or left or right, something like that. And once it moves within this environment, the agent will receive a reward. It's sort of like a reward, some sort of motivation or some penalty for based on whether the action is correct or wrong. So if the action is the correct one, it will receive a higher positive reward. But if it is a negative action, which leads to more negative results, it might get a negative reward. So the agent will try to choose actions which are getting more higher rewards as it is going through this environment. So this process keeps on going on until the particular episode or the loop is finished. So using that, the agent tries to identify what actions and which places give the highest rewards. So the objective in a particular reinforcement learning problem then would be to learn a policy to indicate the best action to take in each environment state, so that it can try to maximize the cumulative reward over time. So what we mean by a policy is that for each particular state in the environment, the agent is able to identify what is the correct action to take. So it's trying to learn while being in the environment. And so it is because since it is like a semi-supervised learning, sort of like a middle point state of the supervised and the unsupervised categories we saw earlier. Because here it does not actually have a particular right or wrong path, but it is learning using the environment data given. So therefore, it has its own particular category. And this is very popular, especially for robotics and game playing and even autonomous navigation, where we try to put agents even within like real world simulations and try to see if the agent is able to figure out what is the most optimal way to go through a particular path and learn how to learn different actions as well. So those are the three main types. And so if you try to summarize what we covered in those three parts, so supervised learning is basically used for label data, and we try to predict that output, which are known as the label. And unsupervised learning uses the unlabeled data, and it focuses on trying to discover patterns. And reinforcement learning will use the data from the environment and rewards and try to learn an optimal action policy. So these are the major three types that we find under machine learning, the paradigms. So far we have come like to the sort of the midpoint of the presentation, the first two sections. So we covered the introduction and the definition for machine learning, and also the main types of machine learning, supervised, unsupervised. I can take a few minutes if you all have any questions based on the first few parts that I have covered. You can either put maybe in the chat, or you can also unmute and maybe ask us as well. I think I can carry on. I think if again, if there are any questions, you can please feel free to put in the chat, or you can unmute and ask as well. So I'll then move on to the next section. So the major part of machine learning will mainly come for how we can process the data. before machine learning purposes. Because we cannot just straight away use the data as it is when we are applying for machine learning purposes. Because data has to be correctly pre-processed, it might have to be cleaned and even prepared properly to be effectively get the high performance that we're looking for. So this is one of the major parts that constitute what we expect to be done in the machine learning workflow. So to give a small introduction into what we can expect from a particular data set, when we're using for machine learning. So most of the time, but at least for most of our cases, basic cases that we'll be using for machine learning, especially in our competition, we'll be finding data within organized as tables. So in this particular table, this is a table of serial data where we have a particular serial in each row, and it has like the details such as the type, calories, the protein quantity, the fat quantity, like that, and the name of the particular serial here. Okay, so what we try to see here is what are the particular the characteristics we can see in a particular data set. So one thing is the data sample. So most of the time in your data set tables, one single row we can identify as a data sample or maybe an observation even. So in a data sample, what it has is basically one particular entity within this data set. So this is like basically one particular cereal brand. And in there we have all the information about that particular cereal brand. What is their type, calories, protein, and fat as well. And this is also, I think, a category, I think, if I remember right. Okay, so each single row here constitutes a data sample. So most of the time, when we are trying to do machine learning problems, we try to have as much as data samples and observations as possible. Because once we have a large number of data samples, we can try to learn from larger number of data sets as well. And we can try to learn from more characteristics as well, rather than learning only from a small set of data. So the other characteristic is known as the feature or the attribute. So most of the time in particular tabular data sets, each column we can refer as a feature or an attribute. So it is basically the characteristic for each observation. So if you consider this particular column for protein, this will give the amount of protein for each of the data samples we had. So this can be used as an input for our particular machine learning models. Okay, and likewise, the calories, fat, type also can be attributes depending on the machine learning problem. Why I say depending on the machine learning problem is because if you're doing a supervised learning problem, our target will be also one of these attributes. But that particular attribute will be sort of a special one, which we refer as the target value, and sometimes the label as well, if it's a classification problem. So in here, if we wanted to predict the calorie count for each cereal brand using the other features and attributes, the calorie column will become the target variable. So we try to predict the target variable using all the other attributes and the features for each of these data samples. So those are like the three major features and the characteristics that we can identify within a particular data set. So these features also, we can have different types. And that is depending on basically the data type that is inside that feature. So for instance, we have one main category is the numerical or metric value. So these ones are basically quantitative values that can be measured. And most of the time, these can be represented as numbers or numerical numbers. So the features such as age of a person, height of a person, the salary, temperature, all of these are numerical values. So these ones are quantitative values. And sometimes these also can be either decimal values or only whole numbers as well, or discrete values. The other type of feature is categorical, basically the ones which are not numbers. And most of the time, these are used to represent categories or groups. So most of the times, features such as the gender, the country, or product category can be identified categorical features. And even these features can also have sometimes an order inbuilt. So for instance, one particular categorical variable can be maybe the number of stars it has received in a particular rating for a product. So we know that 5 stars is much better than 4 stars and much better than 3 stars and so on. So even though that is sort of a non-numerical, because stars can be we cannot say exactly 5 stars means it's 5 times better than the 1 star one. It's sort of like a rough estimation on how good a product is. So, but there is a particular ordering in that. Or even we can take the grading in your particular modules. You get you can get a grade, A grade or B grade or C grade for your modules. So we know that the A grade is higher than the B grade and B grade is higher than C. But we do not know what is the actual number, what is meant by A, B, and C. But sometimes categories also can be non-ordered. So ones like gender, country, product category, most of these are non-ordered. There is no particular ordering in this particular category. And so why it is important to understand the types of features is because depending on the different types of features, types, we might have to do different pre-processing techniques before we train the machine learning models. So it is very important to consider these things as well in our machine learning processes as well. So because of the interest of time, I may not cover most of these methods, but it's important to consider, especially when you all are doing your competition. So, but one other thing that we have to consider is also a concept known as feature engineering. So even though we have our data set that we have collected, maybe from Kaggle or from some external data source, not every column in the data set can be used for your machine learning problem. And we cannot even use every column directly as well. We cannot use all of them every time also, and we cannot use the same way as it is as well when we are training models. Because a machine learning model will learn from the features we provide. If our features are not chosen correctly or they are not properly formatted, even a very good machine learning algorithm can even perform badly, poorly. So therefore, feature engineering and the preparation of the dataset is a very important aspect when we come to machine learning. And that heavily impacts also how we can encourage to get the high performance as well from our data. So some common reasons why we need to do preparation is because some of the features can be irrelevant. So most of the time, if you're trying to identify something like the price, so sort of the sales forecasting methods, most of the business data will have like a transaction ID. But the transaction ID is not useful ever when we're doing prediction, because it's just a unique identifier to identify which is that transaction. So features like those will not be required to be used for our machine learning model. Then also there are some features that are going to be categorical, and they're text and labels, which cannot be processed by mathematical models. Because most of the machine learning models are done in a way that it handles only numerical values. So we have to find a way to handle those particular values which are found in text form or in some non-numerical form. And some numerical features can have very large different scales. And what we mean by different scales is some features will have a large range of values. Maybe, so if we consider a salary feature column, it will have very large number of values from rupees 1 lakh to maybe rupees million, a very large range of numbers. But if we take age, we'll only have most of the time age normally within less than 100. So it's a very small scale compared to salary. So when you have numerical features which are having very large ranges and very large numbers, they can sometimes cause a higher influence onto the machine learning model. So sometimes the machine learning model will assume that salary is very important just because the salary value is very large now. So we have to find ways also to sort of scale those values down to an equal manner. So there are methods such as standardization and normalization, which try to bring all those values to one common scale, sometimes from 0 to 1, or maybe even like between -2 to +2, something like that. So there are different methods which can be used for those ones as well. And sometimes some of the existing features may not even capture enough information as well. So that will depend basically on the domain expertise, how well you know the data as well. So some of the features we might need we need to process them in a better formatting way. So for instance, we might have location data, and location data is given in latitude and longitude. So sometimes the machine learning model may interpret the latitude and longitude in a very different manner. Sometimes it might be more useful to represent the latitude and longitude values as distances from a particular point, rather than giving the exact latitude and longitude. So features like that, we might have to sort of change them and format them in a different manner. So this, to recap what we were explaining. So when we take the clean data set, where we try to first remove all the missing data and all the duplicates from the data, we apply the feature engineering, and using that, we can form better features. And using these better features, we can try to get better model performance and get the high accuracy that we strive to do using our machine learning models. So common feature engineering methods that can be done. We can use feature selection, where we try to use only the useful features and we discard the irrelevant ones. So for example, we can remove ID columns. We can also try to identify features which are highly influential as well for the particular model, or a particular target variable. So using correlation or using feature importance values such as SHAP values, we can try to identify whether this feature is useful or not as well for the prediction purpose. We can also use encoding methods. So encoding is basically done to convert the categorical data, which might be text form or some non-numerical form, into a numerical numbers form. So if we had maybe say a color column, red, blue, and green, we can try to represent each color using a particular number. We can represent red using say 1, blue with 2, and green with 3. And we can use methods like that to sort of like convert the categorical textual data into a numerical format. And as I said earlier, we can do scaling, and we try to put the numerical values onto similar ranges. So this was one example that, as I said earlier, where salary values might have larger values compared to the age ones. And we try to scale them down to a common range of values, either proportional scaling and like that. So common methods are like Z-score normalization or even standard normalization as well. And then finally, we can even create new features, as I said before. Sometimes new information can come with these new features. So we, instead of using the date of birth of a person, we can use the current age of the person at this point of time as the variable instead. So these are some common ways we can do feature engineering, and we can try to create better features that can be used for our data set. Some of the methods that I have found useful to understand in a very intuitive manner. So these are not like hard and fast rules, but they are good ways to identify if our feature is useful or not for our machine learning problem. So first you can check is if this feature will contain any useful information for the problem. So for instance, if we know that if you're trying to classify dogs based on their breed, if we know that height is very useful to identify the tall dogs from the short dogs, because there are certain breeds of dogs which are more taller, which certain breeds of dogs which are shorter. So height sometimes is very useful to identify, maybe because if we know that the dog is more than 1 meter tall, this dog must be this particular type of breed. And if it is very short, it's very likely to be another particular breed. So we can also intuitively identify if these features are useful as well, to give us useful information to identify intuitively as well, rather than, even if we cannot say it exactly. There are ways also to identify this exactly as well, using correlation too. And then we can try to also identify, is the information already represented by another feature as well? So for instance, if we follow with the same identifying the dog breed example, so if we try to use height of the dog as one of the features, it might be redundant to again use a feature like the length of the dog's leg. So because most of the time, if the dog's legs are longer, the dog is also much more taller. So using features which are sort of like double, we can consider them as double because they are sort of like very highly correlated and they're sort of like dependent on the other feature. So it is an important concept in machine learning that we try to minimize features which are sort of correlated to it within each other. So we try to have features which are completely different and unique to each other in that aspect. So if we find features which are sort of can be represented by another feature itself, like what I said, like the length of the dog's leg compared to the height, we can just simply take one of those features only for our machine learning model rather than putting both of the features. Because it's also important to try to minimize the number of features we feed to the model, because providing too many features also makes it much more complex to learn the important patterns. And then we can also consider if the feature needs to be converted to another format. So this is very similar again to the concept I told. Sometimes a date of birth can be more useful to be represented as the age or the duration from this particular time. And we can even consider whether multiple features can be combined to provide a more informative feature as well. So this is also very similar to the idea I told about instead of using two features of latitude and longitude, we can try to combine the two together to form a distance metric from a particular point. So we just use the simple distance from a particular point instead of using the latitude and longitude features together. So, and I would encourage you also to check this relevant YouTube link as well. And you can see some more ideas on how we can identify good features as well. But now another important part of machine learning is also a concept known as splitting the data sets. So because we cannot use all the relevant data itself when we are doing model training, because we typically will try to divide the data into separate subsets. So there are three main subsets that we try to do, and sometimes we only use two, but the three total categories that we have or subsets of data. So the first one, as you can see, is the training set. So that is the subset of the data that we use to train the machine learning model. So using that set of data, which is most of the time, this is also the largest set of data as well, that particular set of data will be used to train the machine learning model and try to get the relevant parameters tuned. And in the second set is the validation set. So sometimes in some problems, we do not use the validation set, but in most very complex machine learning problems, we also use validation. So because it is very useful to tune the model settings and even compare different models. And finally, the other type which we must have is the test data set, which is only used to finally evaluate the final model performance. So in a sense, we use the test data set when we try to identify and tell if how well our model is performing. Because this gives like sort of the true performance metric when we are identifying how our models are performing. So the concept here comes due to the fact of what is the purpose of our machine learning model. So you might be asking why we need to do this data set splitting. And it boils down basically to what we try to do. We try to do machine learning for the purpose on how we can train and get a most effective, a most efficient model that can act and perform very well for unseen data. So therefore, what we try to do is, while we try to train on a certain set of data, we try to identify if the machine learning model has learned very well to be able to even understand data patterns from even the unseen data. So that unseen data is what we refer as to the validation data set and the test data set, as we explained earlier. So even though if there's a high chance that the training data set performance is very high, maybe close to 100 or 90%, sometimes when we apply it to the test data set, the performance of the model can drop very much. And that is a problem known as overfitting, where the performance is very good for training data, but very low for test data set. So to be able to identify if our model is performing very well for actually unseen data, we have to keep a portion of our data to be used as sort of like a test bench to identify if it's really able to perform and identify them. And this is, and as I said, it gives a more reliable estimate of how the model will perform in the real world. And this is also down to a concept known as data leakage. So we have to prevent data leakage, because if we use the information from the test data set in the training, we are sort of giving unseen information which the model is not supposed to know early itself. And we cannot get a reliable performance of the data when it tries to react on unseen data. So how we can do data splitting? And as also it's important to remember, the test data set should always be kept unseen until the final evaluation. So there are different ways we can do test data set splitting. So we can do random split, and this is very much suitable when observations are independent and time is not an important factor in the data set. So if we refer back to example data set that I had earlier, the serial data set, the different serials are independent of each other. There is no relationship or there's no time factor within those different data samples in that data set. So we can randomly choose maybe say 60% of those data sets for the training, and the another 20% for validation data set, and another 20% for the final test data set accuracy. I see. Was there a question in the chat? Yeah, I think I'll be able to share the slides after the meeting, hopefully through the organizers, perhaps. Yeah. So yes, so as I was saying, we can try to randomly split the data set as well. So we do not have to take like the top 60% or the next 20% like that. It is very encouraged sort of to randomly split and mix the data set sample so that we are not biasing towards like the very early old data values as well. So the other method is the time split method. So that is the sort of the opposite, where we have to consider the observations in the chronological order formed in the data set. And this is very important, especially in time series data. Why we have that is because the order of the data is also dependent. So in a time series data, we have data, so say, for example, maybe the sales that is occurring in each month. In each month, we have the sales happening. And because it is a time series data, it means that the current sales of the month is dependent on the previous month, and so on. And that interdependency is very crucial to be considered when we're doing test data set splitting. So therefore, we have to always consider to take the oldest set of data for the training in such instances, and then we take the next set of data for the validation, and then the most recent set of data we leave for the testing. Okay, so especially in cases where time-based series data is there, you can notice this, especially if your unique identifier for each of the each time data sample is having a time stamp. In such cases, we'll have to always do a time-based split, because if we try to train using the new data, it is forming an incorrect assumption about how the data is formed over time. So it's important if the data is having some time-based concept, we try to take the most oldest set of data, the first data, as the training, and then we use the most recent data for testing purposes. So there's a question that whether can overfitting and underfitting data responsible for the precisions and the recall of the model results. So yes, I think you can say that. So I think overfitting I have explained during the presentation, but underfitting I did not mention. So overfitting is basically when the training accuracy is very high, but the test accuracy is low. So meaning that it has learned the patterns within the training data very well, but not during the test data set. It has low performance here. So underfitting is sort of like the other end of the spectrum, where even for training, it has low performance, and test data also has low performance. It is very unlikely that test data set has high performance, even though training is low. So in the underfitting, training data will have low performance and test data in low performance in the underfitting case. So when we have these particular instances occurring, the precision and the recall. So these are precision and recall are two model evaluation metrics that can identify if the model is performing well or if the accuracy is going well. So definitely once those features, once those underfitting and overfitting occurs during the data, during the model training, we'll definitely expect that precision and recall that will be reducing as well. So I hope your question is answered. If it was not clear, please let me know. Thank you. Another question, what is the normal target accuracy level for test data? So this is an interesting question because there is no hard and fast rule to say what is the target accuracy that you must achieve in your test data. So in some cases, it is possible to get very high accuracy in your test data, maybe 90%, 80%. But in some cases, it's not possible even to reach even 50% as well. So that is very heavily dependent on your data set. And in some cases, some problems are very difficult as well to get that very high accuracy. And that also can depend also on the type of technology that is there as well. So very often we would say like, if we can get an accuracy of about 80% plus is generally considered a very good model. But it doesn't mean that there is a hard and fast rule to say that 80% is the minimal test accuracy we should try to get. Some problems can get very high accuracy. Very simple problems, it's easy to get very 90%, 100%. So I think a very common machine learning problem that we find on Kaggle, especially for beginners, is like known as the dynamic data set, that we try to predict whether a particular a particular person in the manifest of the ship was very likely to have drowned or not drowned based on their characteristics. So there are people who have predicted at 100%. So one thing is that since it's a very popular machine learning problem in Kaggle, a lot of people know what is the solutions. And it's very likely that there are very simple patterns which can identify if this particular person was likely to drown or not drown. Easy to classify. But some problems are very hard to identify the prediction or even to classify. In such cases, we might not be able to get the 80% prediction even as well. So then some cases, 70%, 60% can also be sufficient values as well. So it will depend on how the problem is given and also what sort of models are provided to you as well. But in most cases, we would try to expect something like 70 to 80% as like the sort of minimal concept to say it is performing well. As a minimal benchmark, we normally say that if the performance is less than 50%, it's performing less than chance. Because most of the time we consider that, it depends. So if it's a binary classification where there's only two outputs in there, if we do by chance, ideally we should get 50% accuracy. If our model is not getting 50% accuracy, that means our model is underfitted very, very badly. So in that case, we have at least get likewise. And if there were three categories, which means that there's a 33% chance we should have guessed randomly correctly. In that case, like the sort of minimal cutoff for that particular machine learning problem task would be like 33% accuracy. So that is like sort of like a rough benchmark to identify. And like I said, there is no hard and fast rule to say what is like the most accurate value. What is the minimal accurate value you should get. I hope that answers your question. Okay, yeah. So then I'll continue with the presentation. So as we were discussing, we were talking about how data set splitting is done. We can either do random splitting if the observations and the data samples are independent from each other. And we can do time-based splitting, especially in cases where we expect the observations to have a chronological order or having a time series data set. So with that, we can now move on to the machine learning workflow. And what is the overall process of how we do the machine learning in different stages, one by one. So I think in your next workshop, you'll be covering a little bit more information about this, but I will also go through some of this information here. So in the machine learning workflow, as I said, one key aspect of machine learning is that we work with data to learn. So therefore, our first aspect starts from the data sets, and where we might have to retrieve the relevant data from our data. And as I said, some of the data is not clean and it has to be processed and it has to be checked for duplicates, missing values, like that. So that is what will be done using the data pre-processing and wrangling stages, where we try to sort of thoroughly check if our data set has all the relevant state to be used for the machine learning model. If there are errors, maybe the incorrect data types, incorrect numbers, and sometimes maybe the values are missing, we'll have to do some extra steps to be ensure that it's correctly processed and able to be used for machine learning purposes. So once the data set is clean, then only we can do the feature extraction and try to engineer the features that can be used as well. So then after that, once we do feature scaling and selecting what features we need, we can complete the data preparation stage. And once the data preparation is done, we can you take that particular pre-processed and extracted engineered data set to be used for modeling. So there we apply our machine learning algorithms. Okay, so you can choose the machine learning algorithm based on the paradigm, whether it is supervised learning you're going to use, unsupervised, or reinforcement learning, and we can choose appropriate algorithm for based on that. And based on that algorithm, we'll try to model the data that we have fed it. And thereafter, we do the model evaluation and tuning using the validation and the testing. And now this is not like a one-step process. We have to do this in a loop. So once we see the model evaluation and the performance, we can identify if the performance is satisfactory or not. So if the performance can be improved furthermore, we'll go back again to our data set and identify if there are any changes that can be done. Maybe a particular feature can be scaled down to a different value, or maybe we could have introduced a different feature, or maybe some feature was not necessary for the prediction and we can remove it from the modeling. And thereafter, we can begin again the modeling process. Sometimes also we can do some changes to the machine learning algorithm as well. So certain machine learning algorithms, there are parameters that should be fine-tuned and changed depending on how we want to do. So for instance, if we try to do a k-means clustering, where we try to guess what are the clusters, k-means will require you to tell how many clusters do you want the data to be formed. Okay, so that is not a value that has to be guessed by the machine learning algorithm. We have to provide to the algorithm saying that we want to predict we want to identify the group 3 sets of clusters or 4 sets of clusters, depending on our domain knowledge, and we can also fine-tune it further as well. So we can also change values like that within the machine learning algorithm as well, and try to hope we can get better performance as well. And once we get that high performance within our test data set as well, then only we can deploy our model and we can apply and monitor it as well. So in more practical scenarios, once we deploy model, we also monitor the performance as well continuously. If we feel like the machine learning model starts to dip in performance, if the performance is now changing and getting reduced very frequently, then it might mean that the model might need to be reevaluated and fine-tuned again. So this can happen because sometimes from when the model is deployed, there might be changes in the dataset which were not known earlier. So once those changes have to be incorporated back to the model, we have to do another retraining process. So like that, the machine learning workflow is like a continuous process. It doesn't stop at a single linear step that goes from start to end. It is a continuous process where we try to keep fine-tuning and improving the model as well as time goes on until we get that high performance at a very long continuous stage. So I hope you understand what is expected to happen in a machine learning workflow and how the different stages incorporate and contribute to each other. So we can highlight a few machine learning applications, some use case studies. So some of the examples that I've also mentioned in our previous slides. So I will go into more deeper in some of the applications here. So one case study I've taken here is to predict the housing prices using regression. So regression, as I saw earlier, it is a supervised machine learning problem. And here our target variable is housing price, which is a numerical value. And it is a continuous value. So therefore, we can use regression for prediction purpose. And now referring to our TPE definition, our task in this particular case study is then to estimate the selling price of a house. And how we check how well we are performing, we check how close the predictions are to predictions of the housing prices that we predict are to the actual housing prices. And we can use a metric known as mean absolute error as well to identify how close the predictions are to the actual housing prices we have predicted. And what is the experience we're using? The data set. The data set of the house location, the build features, and their pricing. And for features, we can use different features such as the floor area, number of bedrooms, the age of the property, distance from the city center, and we can even generate more features as well, depending on the data we have here. So we have to also continuously keep on selecting and identifying which features are important. In some particular cases, we might have that the distance to the city center is not a useful feature for the housing price. For instance, maybe housing prices are not influenced by the distance. So in that case, we can drop the feature like that and should see if there are any other more important features which are influencing the housing price. So another case study is the customer segmentation or clustering. So clustering, as we said earlier, it's an unsupervised learning method where we do not have the particular cluster, we do not know what are the clusters or the groups that we are trying to get for. And we try to group the customers with similar purchasing behavior in an e-commerce site. So the purpose here, in most cases, especially for e-commerce sites, is like to identify what sort of groups of customers are there. And once you identify a group of customers, you can try to give solutions and recommendations to that particular group rather than giving solutions for each and single individual person. So those are some types of uses of using customer segmentation with machine learning. And there, our performance metric is then to see how closely grouped the samples are within a cluster. So for that, we can use a metric known as inertia or within cluster sum of squares. So basically, that will check whether how close the data points and the data samples are within a particular cluster. If you find that the data samples are very far spaced out within the cluster, it might indicate that the cluster is not appropriate because it is very large and spread out. But if the data points are very close to each other, we can identify that this could be a very good cluster because most of the data points are very close to each other and very similar to each other. And likewise, the experience is basically the data set of the customer behaviors based on how much they're spending, the types of items bought, time spent on the website, etc. And we can use those features as well. And since this is an unsupervised learning problem, we do not have a particular target variable, but we might have to identify what sort of number of clusters are we going to form. So most of the time we start with 3, 4, or 5 clusters, and we keep increasing until we find whether it is not useful or more to keep going. Okay. Sometimes we go the other way as well. And we use a method known as elbow method, which I encourage you to read up and check as well on how we can identify what is the ideal number of clusters and groups that we can use for a particular problem. So as I'm nearing the end of the presentation, to summarize what we have covered, so we saw that machine learning enables computers and machines to learn patterns from data, and the main types of machine learning problems can be given as unsupervised, and reinforcement learning, and they try to address different types of machine learning problems. And a well-prepared, clean, and prepared data set with the features is essential to make effective, high-performing models. And the machine learning follows a structured workflow from data to deployment, and it is also a continuous workflow. And finally, the machine learning can provide a wide range of real-world applications and predictive solutions. So with that, I conclude my presentation. I hope you will manage to learn something. So if you have any questions, I'll be happy to take them down. I've requested my email. I'll share it with the slides, I think, through the, perhaps with the committee. Okay. Okay, there's a question, how to decide the most suitable machine learning algorithm for any problem. Okay, how to decide the most suitable machine learning algorithm for any problem. So we have to think in different aspects, definitely. And also, I think the core thing will come is, what do you know? What is the problem state? What are you trying to do using the machine learning problem? What is your task? So that is why I wanted to highlight the TPE concept. So I just verified from the person who asked this question, do you want to know like what is the most appropriate algorithm to use? Like maybe not the particular category supervised or unsupervised, but do you want to know what type of machine learning algorithm to use? Vishwa, I think, is the person who asked the question. So is it possible for you to elaborate what do you mean exactly by the most suitable machine learning algorithm for any problem? Like what sort of machine, which way are you hoping to answer, want me to answer this question? Okay, seems like I'm not getting a response, so I'll answer how I can. So the question was how to decide the most suitable machine learning algorithm for any problem. Okay, so I think here the key idea I would try to refer first is, first we had to consider using the TPE format, whether what sort of machine learning algorithm problem are we trying to do? What is the task that you're trying to achieve? So when we have considered task, so if you're trying to predict a particular numerical value, it was very likely going to be something like supervised learning algorithm. And if you're trying to do maybe some category, trying to identify a particular category, then we can use classification. Or else if you're trying to do something like we do not know what we're trying to look for, but we're trying to look for patterns and relationships, then we tried unsupervised learning methods. So if the particular person who was asking this was referring to the particular specific algorithm to use, so obviously we can go for the most powerful algorithms first, and we can try to simplify them. So I'll give you some key insights which I could explain about. So if we are having some linear type data, if we know that the features are related to each other, to the target variable in a linear format, one very good algorithm to use is linear regression models. So I think I had a diagram here. Yeah, right here. So this is just a diagram of how linear regression would perform, right? So in there, we might expect that the independent variables, the features, will be directly correlated in a linear format, so that as we increase the particular independent feature, it will also increase the target variable. So if that is the case, then linear regression is a good model that can be used, even though it's a very simple algorithm. But in some cases, and especially very complex data sets, we might not get this linear pattern of data. It is very hard to get. Maybe the data is like non-linear, having curves or having different shapes and like that, so on. So then we might have used more complex algorithms. So one method which I kind of hinted at under deep learning was neural networks. So neural networks are a very high performing, much more able to achieve patterns which are not linear even. And even more than that, we can go to things like XGBoost, random forest as well, which can also be used. Even they are also linear, but they also are much better than simple linear regression. So if, for instance, if you have a linear data set, maybe we can start with the linear patterns first, the linear regression or decision trees or random forest first. And if they are not performing well enough, maybe then we can try to go for neural networks. If we know that the data set itself doesn't have any linear patterns, then we can go to neural network-based methods straight away instead. So that is one sort of aspect that you have to consider. So it is okay to go first to the most complex methods. I think, especially in a case where you're not trying to get the highest performance, you also try definitely to take the most complex algorithms possible, such as random forest, XGBoost are the most common ones which are used. And I think, especially if you're going to do time series problems, there might be more different models, such as SARIMA models as well. So it's okay to try these more complex models and formats instead. But if you feel like it's not performing well, sometimes it's important to go down to another level down to more simple algorithms, because sometimes it might have a very simple pattern that is required just to be identified instead. So I hope I was able to answer that question as much as I could. So I'll move on to the next question. Can a single real-world application use supervised, unsupervised, and reinforcement learning together? So this, I'm going to incline to say no, but you can define it like this. So if we consider machine learning case study, like for instance, maybe we were doing for an e-commerce website, maybe my case 2 study in here. So this particular case was definitely for an unsupervised learning method, right? So, but I can also make a supervised learning problem here as well if I wanted to. So, but if I wanted to try to predict how much a person spent based on the number of items they bought and the time they spent at the website. In that case, I'm doing a supervised learning problem, but for the same data set, but it's a completely different problem I'm trying to solve at once. So in a way, I would incline to believe that we can only have one type of paradigm that we could use, one sort of application that can be used for a single machine learning problem. So a machine learning problem might try to use maybe a supervised one if it has learned the label data, or maybe if you're trying to find patterns, then we use the unsupervised one. But we can use all three methods definitely within the same problem, within the same domain and the case study. So for an e-commerce website, I might use the supervised learning to see if I can predict the amount they spend, the customer. But I can also use the unsupervised method to group those customers into different categories. And if I want, I could even use those grouped clusters as well as another layer. So I can even feed that also as another layer into my supervised learning as another feature to say that I have identified this particular group of customers as cluster 1, cluster 2, so on. And that particular cluster, I have seen that they are very high cost, they are very high spenders. So sometimes like that, that is also very useful to apply as another feature. Even though we are not using for the exact same problem, we are not applying all three at once, we can combine those ones together in an overall case study of the data. Reinforcement learning, there are possibilities, but most of the time, reinforcement learning behaves on its own separately. Sometimes it does go along with supervised learning, but in very common use cases, it's much more independent differently because most of the time it is done for activities such as robotics and agentic applications instead. So I hope I've answered your question. Okay. Are there any other questions from anyone else? Okay, maybe wait maybe a minute or two in case another question comes, or else I can hand over back to the organizing committee. Seems like there are no more questions coming up, so I think I can conclude my presentation. So thank you to everyone who's listening, and hope you managed to learn something for your competition. I wish you all the best for your competition as well. Thank you for taking part in this webinar.
Thank you very much, Mr. Navindu, for that insightful and inspiring session. As there are no further questions, we will conclude today's workshop. Once again, on behalf of the IEEE IAS Student Branch Chapter, University of Moratuwa, I would like to extend our heartfelt gratitude to Mr. Navindu De Silva for taking the time to be with us today and for sharing his valuable knowledge and experiences. Your insights have undoubtedly inspired all of us to explore the fascinating world of machine learning with greater confidence and curiosity. Please accept this virtual token of appreciation displayed on screen as a symbol of our heartfelt thanks. To all the participants, thank you for joining us and making this session a success. We hope today's workshop has given you a strong foundation as you continue your journey through OctWave 3.0. Stay connected through our official communication channels for updates on the upcoming workshops and competition activities. Have a wonderful evening, stay safe, and we look forward to seeing you at our next session. Thank you, everyone.